That's great. Well, my name is Nandini Trivedi from stage to tell us about fractionalized excitations. Thanks so much. I just talk loudly. If the audience is okay with you talking? Hello? Can you hear me? Okay. Okay, good morning, and thank you all for bringing me along for inviting me. We've done so much and have wonderful interactions. I want to talk to you about quantum state liquids. Specifically, they are characterized by low-range order. And with that, they don't have the standard excitations which are magnons. They are fractionalized excitations. And I want to make two proposals for how to detect them, especially because there are experimentalists here, and I think that would be very helpful to have more discussion. Okay, let me first thank all my collaborators, and also the references are on this. So Xie Feng is my graduate student who is just moved on to a postdoc at TU Munich. Collaborators Adit Agrawal and Shubhra Bhattacharya from Kanpur and Bangalore. And more recently, Peng Hao Zhu is a postdoc at OSU. And we've been using different methods in doing these simulations because we need different degrees of fineness to them and exactness to them. So from exact diagonalization to all of these, what is going on? It doesn't seem to show up. Okay, different techniques. And more recently on the IDMRG and IPEPs, we have collaborated with Tao Xiang and Kan Wang from IOP. And then towards the end, I will talk about some unpublished work with my graduate student Ryan Buchanan and Xu Yan. So that's the plan. And I'll be, I want to get only the main ideas across because time is short. So the first point that we see with quantum spin liquids is we are in a very interesting regime where in materials and only in collective interaction systems, it doesn't have to be materials, it would be like cold atoms and other situations where your entities interact strongly, that we see fractionalization of something that is a fundamental entity like an electron, which carries charge and spin, and that can separate in a Mott insulator. And furthermore, we see some of this physics in Mott insulators and also in the quantum Hall effect. But what you get further in a spin liquid is that the charge and spin get separated. And now even the spin can get further fractionalized into these anions. So in a way, because charge and spin have been separated, the response can be more focused in the spin sector. And the question before us is, can we detect these fractionalized excitations? And even more significantly, can we find a sharp signature of these fractionalized excitations? Okay, so starting with the standard probe, which is neutron scattering, you bring in a neutron and it excites these collective magnon modes. And in a system like La2CuO4, which has long-range order, these are observed as sharp modes. And you can map out the spectrum. And this is the standard way to probe magnetism in spectroscopy. But now, if you have something like a spin liquid, like alpha ruthenium trichloride is a candidate material, here I'm showing you the results from a simulation of a model. And you can see it's a complete washout. There is nothing sharp sitting in this signature. And that is an indicator that the magnons have fractionalized. But that's not good enough. We want to see if there can be something more sharp about this that we could identify. So in my talk, I'm going to present two ideas. And I'm going to go toward multi-spin correlators. So neutron scattering is essentially a one-spin process. So it's a two-spin correlator. And I'm going to go toward higher order correlators. And what I will try to show you is that there are indeed sharp signatures, and I'm going to present these results through just one particular model, the Kitaev model, but because that's where we can calculate things very accurately. But the lessons we learn from that are much more general, and we are extending it to more general Hamiltonians. So I'm going to show you how you can see the anion dispersion, and that could be observable by NV spectroscopy. And also in pump probe nonlinear response, this is even more exciting, not just the signature of fractionalization, but even the grading statistic, because ultimately the anionic aspects are coded in the way these fractions braid. So that's my plan. And so let me start with the Kitaev model. I think all of you know that, but it's defined on a honeycomb lattice. And these, on the sides of the honeycomb lattice, you have a qubit. And this could come from spin half, or it could come from J equal to half if you have spin orbit coupling. In a material, you necessarily need spin orbit coupling to produce the kind of interactions which are very anisotropic. So every bond has different Pauli matrices that are interacting. Either it's the X1 on the blue bonds, or Y Pauli matrices on the green, or Z Pauli matrices on the red. Now, what is interesting about Cloquet and synthetic platforms is that we can, there are ideas to construct such a bond-dependent interaction Hamiltonians just using Cloquet dynamics and without any spin orbit problem. And it's important to keep these different platforms in mind because each one has their own advantages. Now, beautifully, Kitaev showed by an exact solution that this model has no long-range magnetic order. Instead, it has topological order, and which is characterized by long-range entanglement and fractionalized excitation. So that's very important. We have a model that we really understand well, and now we can go away from the exact solution limit. Okay, now I just want to flash the key ideas behind this Kitaev model. What are the ingredients going in? And this translates into other models, which may not be Kitaev, but other magnetic models. So one key ingredient to getting a spin liquid is that you need frustration. And that shows up here by that central spin that I have highlighted, having three contradictory instructions from the three bonds to align along X, Y, or Z. And as a result, that central qubit is frustrated. And the consequence of that, so in different magnetic models, the origin of frustration could be different. It could be competing Heisenberg interactions, even in band models, it could be that a kinetic hopping is frustrated. So the origin of frustration can be different, but the pathway is very similar. So because of frustration, this spin degree of freedom now fractionalizes into, in this case, 4 Majoranas, and 3 of the ones which are judiciously colored form the link variables with with the red and the other links. And that should remind you about A dot dl from your ENM. You're basically picking up a flux as you go around the plaquette. So what has happened is the spin has fractionalized, and it has created 2 new degrees of freedom, the fluxes as you go around the plaquette, and the black Majoranas, which are now itinerant and give you a spectrum very much like graphene. So spin was a localized entity, but the emergent degrees of freedom are gauge degrees of, you get a gauge theory, and you get an itinerant Majorana coming out of these localized spins. So this is a very evocative picture. And the question is, can we see some of these signatures? So here is our proposal that if you take, let's say, compare a Heisenberg and a Kitaev magnet, In a Heisenberg, which is ordered, one spin flip, which is this correlator, the usual S of Q and omega, is sharp. The Kitaev, on the other hand, I showed you, was that very broad featureless spectrum. But if you go to the two-spin flip, which is this correlator given in the bottom, it is a dimer that you flip at, say, time 0, and then you flip it back at some later time. And from that, you construct S2 of Q and omega. That is a broad signature for an ordered magnet, because you're essentially creating two magnons, and these two magnons can share energy and momentum in multiple ways. So for an ordered magnet, this signature is broad. And what I will show you, rather surprisingly, for the Kitaev magnet, this two-spin flip is a sharp signature and also directional. So it's a very particular signature that, if observed, would be a direct proof of such anionic excitations. I don't want to go into this phase diagram, but just this simple model with Kitaev and a field. So now we go away from the exact solution, which exists only at zero field. I still don't know why. Okay. Light matter interaction. Okay, so H equal to 0 was the exact solution. When you go away at finite field, and also the vertical axis is by strain, you can tune the strength of the bond interaction, the exchange interaction. You get a very rich phase diagram. And the only thing I will need for today is that kind of in the lower quadrant here, you basically have the gauge and matter degrees of freedom both interacting. As you go away at large Kz, the Majoranas get highly gapped, and you have only the gauge degrees of freedom, and that is a toric code limit, which we understand well. So that's a region that I will focus on. And further, another very exciting thing we found is when you take this Kitaev magnet and you say, well, let me turn on a huge field, you would expect the system to just get polarized. And we do see that at very large field here, but surprisingly, a gapped phase goes into another gapped phase through an intermediate gapless phase. And that is also a very rich area of why you get this gapless phase. But I won't go into that today. Okay, so let's try to understand here why two spin flips is creating something, something sharp. What is the main idea there? So the main idea is, let's say you bring a neutron which interacts with the system, and in a one spin flip process, you create basically a combination of fluxes and the Majoranas. Okay? So it is mixing up both of these degrees of freedom. But what I'm going to show you is that when you do two spin flips, it has this ability. So this is just reiterating the one spin flip now. So the one spin flip has been done on, say, one side of the honeycomb, and it has created that pink Majorana. It should have been black to be consistent with the previous picture, but it's that same itinerant Majorana and the two fluxes in the adjacent plaquette. When I now create, and now I do the same thing on the upper side, and again, there's a Majorana and two fluxes. Now I create two of them. So what that does is the two of them together create two fluxes in each plaquette. But this gauge theory is a Z2 gauge theory. So two fluxes is equivalent to zero flux. So by doing two spin flips, I've managed to erase the effect of one of the degrees of freedom and now only have the Majoranas contributing. So in a similar way, in other Heisenberg problems, where you create strings, and that's why you get broad responses, by doing two of them, the string gets erased. So that's the main idea. Okay, and Now, moving into the limit where only the gauge degrees are contributing. So I showed you how you can have only the matter degrees contributing. Let me now go into the toric code regime where only the gauge degrees are contributing. So here, the way you get toric code very quickly is that you start with this honeycomb lattice, and if Kz is large, then you can look at this bond and define new qubits in the low energy sector. So here my K is antiferromagnetic. So I'm defining a new tau qubit, which is up down on this link plus or down up. And that is the tau qubits now. And in terms of tau, in fourth order perturbation theory, you get an effective Hamiltonian that has the star operator and the plaquette operator. So the star operators are made of tau x across, so you should think of this square lattice, this emergent square lattice, as my toric code lattice. And on that, the tau operators, tau x operators give me the star, and the tau z operators around a plaquette give me the B's or the fluxes. Okay, now one spin flip will take me into a high energy sector. And when I do two spin flips, I return to the low energy sector. And we'll now look at the dynamics in the low energy sector. So to get dynamics, I add a field perpendicular to the plane. And this field, when you go to fourth order perturbation theory, shows up as the third tau operator. So remember, the star was made up of tau x, B was made up of tau z, and now the field appears as a tau y. Yeah, sorry, Marcus. Yeah, the field in the original Hamiltonian, this one, is applied in the 1-1-1 direction. So it couples to all the three Pauli operators. Yes, it is important. The direction of the field is very important. The results are quite different when they are in the plane. And even in the plane, it depends whether it is in the zigzag or the armchair direction. So I won't discuss that today, but we have papers on that. Okay, so now let me first show you what happens with what I'm showing you now are the results of two spins. So I'm doing this. I am, okay, let me start here. So this is the quantity I'm calculating. I'm looking at a dimer here. So let's say the Z bond on which I'm flipping sigma x on a Z bond. Okay, so that's my dimer. I look at this dimer at time 0, dimer at a later time, Fourier transform, and that gives me S2 of K and omega. Okay, so S2, and I sum over K, just to make it just look at the integrated weight. And if you were looking at the Heisenberg, you see this broad feature as I had mentioned before. So this is as a function of omega here, and this is for different fields. Now, if you look at the Kitaev, what you see is it has, so let's pick a certain field, you see many little peaks, and that is a signature. So you don't see a lump, you see many peaks. And that is a signature that your mode has fractionalized. And furthermore, if you see the energy scales are different. Here it's of order the exchange. Here it is 100 times smaller because that scale is coming from the fourth order perturbation theory, and it goes like k to the fourth by kz cubed. So there's a lower energy scale. And moreover, if you fix your energy at the peak, you find a very sharp dispersion of these fractionalized modes. So you see that it has a well-defined momentum. And you might ask, how is it possible? Why is this mode not sharing energy and momentum between the two fractions? And you can see the reason from this animation here. So this is that toric code. This is a E particle and an M particle. These are my two excitations. And as I turn on a field, that field generates a dynamics for these excitations. So you see they move like this. Either you can think of the original honeycomb or you can think of the underlying toric code. So they move together in this very coordinated way. If they had randomly moved in arbitrary directions, the signature would have been broad. But the point is that because of the gauge constraint, the two fractions have to move together. And that's the origin of those sharp features in momentum space. And I showed you several peaks. Sorry, go ahead.
Could you remind us how the cows were defined? I think it was comments back.
Yeah.
Sorry, during
Yeah, sorry. So the tau was basically so the original qubits was sigma at each site here of the honeycomb. Now you take the two qubits sigma on the bond, and you just look at the subspace of the two qubits on the bond, and that will be up, down, or down, up. And you define a new qubit tau based on that link variable. Okay, and then you do fourth order perturbation theory to get the square lattice effect.
The NISOC field of dispersion again?
Yes.
I guess I wanted to ask is, so that's just set by the underlying Kitaev interaction. That doesn't have to do with the direction of the magnetic field?
The modes will be totally different if the field was in the plane.
Sure.
Yeah. Yes, but this is basically from the Kitaev interaction.
Then why is there not like an equivalent dispersion?
Oh, there is. Yeah, there is. I've just broken the symmetry to just show you, but there is another equivalent mode at the other diagonal.
So in an experiment, you'd see a mixture of these.
Yes, but if you, yeah, that's right. That's right. Okay, so that would be one prediction, is to look for such a two-spin excitation, and you can do it either momentum resolved, but if it is not momentum resolved, even that has certain features. So Raman would be like the first thing that could be tried. And I wanted to say that these peaks have very particular signatures. So I just showed you the first one here. Each peak here has a certain imprint in momentum space. And like this one the first one has this imprint. The second one is a different excitation because as you go up in field, at some point, the Majorana mode, which I said was gapped out and not playing a role, comes down in energy and mixes with these E and M excitations, and that produces some hybridization. And in the spectrum, you see certain gaps because of the hybridization. So that's another thing that could be observed.
To understand correctly, you introduce perturbation with dynamics to the E and M, and at the same time you create a balance state between E and M. Is that robust? I mean, you could make another perturbation, maybe it gives dynamics of no balance state.
The bound state is coming from a very strong gauge constraint. So you could put in other interactions like Heisenberg and so on. They will just produce a broad background. And I'm writing on top of that, there will still be this sharp feature.
So you say bound states are generic?
Yes. Yeah. Okay, now let me get even bolder and ask, can we see the statistics of these fractionalized excitations? And now I want to look at something like this. If you create these E and M particles, if E braids around another E, that is just bosonic statistics. If M braids around M, that's also a bosonic statistics. But if E braids around M, so a charge goes around a vortex, then you get a minus sign. And the question is, can we see that? So here is our proposal. Let me just very quickly review the linear response. So in linear response, what you're going to do at t equal to 0, you'll take your system and you will perturb it. You'll probe it. That's the perturbation. And you'll apply a field that couples to the magnetization. So M is the magnetization along some direction. At a later time t, one would measure this magnetization along a direction beta. And so the linear response chi alpha beta is this commutator. And for the toric code, one can show that this commutator has a sinusoidal behavior in time. And that's just given by the frequency is given by the gap to create the pair of anions. And there's a further decay, which goes like 1 over t, and that is the probability to find the two anions to be at the same place. So, at t equal to 0, you'll create the anions. At a later time, you'll annihilate them. And that probability decays as time goes on, because if these anions move away, then you have to still bring them back to come back to the ground state. Okay, so that's why there's an amplitude which decays with time. Now, in nonlinear response, we have one additional step. First, we pump the system into some excited state. And then we repeat the same thing. You again perturb it or probe it at a time t1 and measure at a time t2. Okay. So again, not to go into details, just to show you that you're starting in the ground state, you're pumping it to some state e to the IH magnetization. And then you are measuring in the pumped state. Now you do basically like a linear response measurement. So that's this correlator of two magnetizations, and then you come back. And then from that, we subtract out the linear response to get the pumped response. And here we have there's a beautiful paper by Sid Parameswaran's group that we were very influenced by. And in this, now we can look at it in an expansion in the field and look at it to order h cubed. So that I'm going to denote by chi3. So I'm going to look at the nonlinear response, which is the response to order chi3. Okay. So let me go a little quickly. But here's the main result, that when you look at chi3, it becomes, it involves these 4 magnetizations now. And you can show that chi3 will have a piece that goes like chi1 times T2, which is this time, the measurement time compared to the pump and probe. So really, it will depend on this tau 2 as T to the 3 halves. Okay. Now, let me tell you I want to show you the main result. First, let me tell you the main idea. So we are going to do 2 experiments. In one, I'm going to apply the field always in the same direction. Let's say X, 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 X. All the magnetizations are in the same direction. And what that will do is it will create either E particles or M particles, and they will just braid around each other and give you bosonic behavior. So that will be our control. Next, I'm going to do something like this, where the first one, Mx, will commute with the star operators, but it will create 2 M particles at 0 time, right here. Then at a later time, when I will apply the non-commuting MZ. So MZ will commute with the plaquette operator, but it will create now 2 E particles. And then on this time T2, these M's and E's will braid around each other, and that is where it will produce some signal, which the chi3, which involves the same magnetizations, will not have. And what is that signature? That signature is shown here, that if if all the magnetizations are in the same direction, so all your fields are in the same direction, it produces no braiding, and you basically see a sinusoidal behavior that decays with time. On the other hand, if you take these fields which are in different directions, so the operators involved are not commuting, you create E's and M's that braid, and it gives you an additional term in the response. In addition to the decaying term, there's a C square root of T, which is growing with time. Of course, it can't go on forever. It'll start decaying at some point, when the E's and M's lose coherence. But there is an intermediate time scale where the signal is very different and now increasing in time. And so that is the signature of braiding that we would like to propose. So the main message is that instead of doing 2D coherent spectroscopy where you Fourier transform the signal, look at it in time and try to disentangle this additional growing signature. And with that, let me come to the conclusions. As an outlook, we need more quantum materials. We are limited to just one or two. We need synthetic platforms to create such models. And I want to propose new types of probes going beyond one-spin flips to see fractionalized excitations and their braiding statistics. And I haven't talked about this, but there are very close connections of these strongly coupled Hamiltonians with just the band structure, which can also produce frustration. And then looking at flat bands that come in this other extreme limit when you, the same processes that give you Kitaev antiferromagnets also give you very flat bands, rather interestingly. So with that, let me thank you.
So that's the perfect segue into our next part, which I think is about new quantum materials and flat bands. So please come up and set up, and in the meantime, I know there's already been lots of great questions, so.
I was just curious, so what energy scale do you expect this to?
Oh, energy scale. Yeah, just 1 second. And thanks for that question. It was here. So the energy scale is set by J. And the time scale would be basic. So I've just taken something like 1 millivolt. It could be, J's 10. So this is about 10 Kelvin. And it gives a time scale of about femtosecond or.
I'm curious if you could compare it with Canada, or
Okay.
the speed rate are typically around like 10 level. With double magnet excitation,
Yeah, it's reduced by about a factor of 10. So 1 millivolt.
Really?
Yeah.
People must have probably the data already.
Yes. So the ruthenium trichloride is not a perfect Kitaev. It has the Heisenberg competing interactions. So, but that doesn't spoil our result, because what it says is the Heisenberg part will just give a broad signature, and riding on top of that will still be a sharp effect. So it is a matter of maybe looking precisely at lower energies than people have looked. Yeah.
Do you have any sense of how much spectral weight will be in the sharp peak as opposed to the incoherent factor?
I think one could estimate that right now because we didn't bother. In fact, we have these two separate calculations, and in a way they are not going to be interfering, because even though I said there will be a broad that background is of much higher energy. So at these low energy, there is actually no energy.
I show you how to do it.
You don't have the link?
I don't have the link. Then I send the link.
Yeah.
The physics behind
You can-
where the
Oh,
scale confusion is.
Yeah.
What's the
So
link? And then I have the
the
link.
decay is one of the things.
你需要被 record 吗？
The
Oh,
key to the three
you did
parts
that, okay,
comes
record,
from the
record.
fact that you
Oh, what's the way I'm
this grading,
你给
which
发我。
which
Email.
basically subtends an area. That's the
或者
area
你能直接听那个中吗？
graded. And that area has two dimensions. One grows like T2.
你想
That's
跟
the
中
time you are allowing it to propagate. And the other dimension has a square root of
或
it.
者就
So it goes like T2, which is the time you're evolving to the power 3 halves.